we're looking at combinations. So let's explore for a second. We already talked about it a little bit in the last lesson. So how many ways are there to arrange A, B, Z, Y? But keeping A, B in order. Now, generally speaking, you'd think there was 4 factorial ways to arrange it, right? But we're going to do, keeping A, B in order, we're going to do it like this. So the first thing we're going to do is making A first, right? And then A, B will be in order no matter what. So there's 3 factorial ways to do that, right? To arrange. So we put B first, and then we do Y, Z, right? Then we do, and sorry for this if it's boring, you can skip ahead and just trust me that I wrote every combination keeping A, B in order. But I put Z first, and then I did YB, then BY, then Y first, and then BZ and ZB, right? And I'm doing it this way for a reason. Then I put Z first. I let Z be first, and then I let Y be first, right? Obviously, B can never be first because A, B have to be in order. So then I said AB, then Y, then A, YB. Then I put Y first, and there's only one combination I can do. I can't say YBA. So next I put A first, and I said BZ, then ZB. Then I put Z and put AB. Now, that's every combination. There's 12 where AB is in order. But for every way AB is in order, if I include, there's a situation where B and A are out of order. Okay? So for every one of these, I can switch BA out of order, and that gives us 12. Remember when I said the total ways is 4 factorial? Well, that's equal to 24. And there are 24 ways in total, right? So for every one of these, there's another way. So the total arrangements is 4 factorial, but we can divide that by 2 factorial. Divide it by 2 because for every way there's another way, right? AB can be arranged in 2 possible ways. So I divide by 2, or 2 factorial, and you'll see the difference why it's not just 2 and 2 factorial, even though they're the same. Okay, when we give another example. What if I also wanted YZ in order? Okay, so if I wanted, this is the number of ways AB is in order. So I discount that already with this 2 factorial. Divide by 2 factorial for the BA to be in order. But for every YZ in order, there's a ZY out of order. So I can divide by 2 factorial again to arrange the ZY. And if we look here, this is a situation where ZY is out of order, and this is its matching case, right? It's almost the same, except one is in order, one's out of order. ZY's only. See there's a ZY, and here's YZ. So I cross one, and I keep one. And I continue on, and I see that I crossed out one. Every time I cross one out, let's clear the markings so you can see properly. Every time I cross one out, I circle one, right? These two match, these two match, and these two match. Okay? So N, AB, and YZ in order is 4 factorial over 2 factorial. So it's almost like the same formula where AB was the same. It's almost the same thing as saying AA. How many ways are there to arrange AA and ZZ? If order doesn't matter, in this case, the order of these A's don't matter. It's the same principle that we divide by 2 factorial. So it'd be 4 factorial over 2 factorial times 2 factorial. Same, because the order of these don't matter. Same thing with, if I want to keep them in order, then I don't want to count the ways that they're out of order. So I divide by 2. Hopefully that makes sense. How many ways are there to arrange ABZY, keeping ABY in order? Okay, what if I want ABY in order? Well, you just do 4 factorial over 3 factorial. Now, for every ABY in order, there are 3 factorial ways to arrange ABY within that. And that's why we divide. So I'm gonna show you how that is right there. ABY is in order. Yes, if we keep ABY is in order here, and I keep the Z back there. Okay, but there are 6 ways to arrange ABY all going down there. 6 ways to arrange it. Okay, so I don't want to count them. Then I put Z in the middle. I put Z here, third. And if I look at that Z, only one of these ways has ABY in the middle. Makes sense? So I don't count those. And here we have Z second. And I put Z second for all of them. But only one of these has ABY in order. And finally, we put Z first. And only one of them has ABY in the middle. In order. So what does that mean? Well, this is 4 factorial. There's 24 ways, which is 4 factorial ways, 4 letters, but 3 factorial of them don't count. Right? Sorry. For every single one of these, for every way that they are in order, for every way to arrange these, where ABY is in order, there's 6 ways to do that they're not in order, or the 3 factorial ways. So we divide by 3 factorial. Okay? Now here is a combinations formula. The number of combinations of our objects chosen from a set of n items is, and you should probably remember this formula. Now, if you remember, this is the formula for P and R. So we just divide by R factorial. And maybe it makes sense to see it in action. So let's give an example. In a game of poker, a player is handed 5 cards from a deck. How many ways can this occur? Previously, what we did was we said there was 52 cards, 51 cards, 50, 49, and 48 ways. If order mattered, if I was like first, second, third, right? But if I find myself with 5 cards suddenly, right? I could find myself with these cards, or I could find myself with these cards. This is just an example, right? But if I say order doesn't matter and I'm going to count them as the same, well, it will count these as different. So how many ways are there to arrange these 5 cards? Well, there's 5 factorial ways to arrange it. So every hand, every single possible hand is counted 5 times. So initially that's 52 choose 5, but if I divided every one of those, okay, there's 5 factorial ways to arrange them, so I divide it. If I say, well, order doesn't matter, I divide by 5 factorial. I don't want to include it. Okay, so it's basically 52 factorial over 52 minus 5 factorial over 5 factorial. That's basically CNR. 52 choose 5. So there are 2,598,960 ways to get 5 cards from a deck of cards. All right, next. It's a cooking competition. And we need to make gourmet soup from 10 ingredients, but we are going to only include, and we must include, 5 ingredients. So how many different soups? Or it doesn't matter in a soup. Let's just assume that's true. So it's basically 10 choose 5. 10 factorial over, remember, it's n factorial over n minus r factorial over 5 factorial. Of course, you have this button in your calculator. So the answer is 252. 252 soups can be made. Okay, so Ainsley is making a platter of 4 types of caviar and 4 types of Blinus. She has 7 different caviar and 6 different Blinus. And how many ways can Ainsley make the platter? So we will consider each group separately. So choices for caviar times choices for Blinus, because for every choices. So for every single choice of caviar, there's however many choices there are for Blinus. So we multiply, we don't just add them. So it's 7 choose 4 multiplied by 6 choose 4. Okay, so it's n factorial over n minus r factorial times 4 factorial. We end up getting 525. If you pump this into your calculator, check to make sure you're using your calculator correctly. So 525 platters can be made. Finally, 7 points represent cities in North America. How many paths can be drawn by joining pairs of cities? 1 pair, 2 pair, 3 pair, 4 pair, 5 pair, 6 pair. Basically, AF, how many ways can you select? 2 out of 1, 2, 3, 4, 5, 6, 7. Well, if I said P, 7 choose 2, that would give me, the number of ways I can arrange, all of them. But it would also include AF would be FA, right? And joining doesn't really matter, although the flight might be different, but regardless. So what do? We do 7 choose 2. Whoops. And we get 21 different ways. Now, if you want to make sure that that's the case, we know that there are 6 paths, followed by, from F to the rest is 5 paths, plus 4, plus those 3, plus 2, plus 1. And by the way, that equals to 21. So, oops, plus 3. Whoops. Let's clear that. Anyway, 21 paths to the cities. Convince yourself of that. And that's it. Homework will be posted on the class site.